Hey everybody, so this is the final part of the first revision lecture, and this time we'll be looking at valence bond and molecular orbital theory. So here's the overview picture that was in the last lecture as well. Last time we focused on Lewis theory and VS-EPR theory to determine the types of bonds between atoms and also the shapes of molecules, but this just assumes that the bonds were shared electrons between two atoms of the molecule and didn't describe at all how these bonding pairs exist. So today when we look at valence bond theory and molecular orbital theory, this will really describe the sort of molecular orbitals where these electron pairs of the bonds exist. So valence bond theory takes things one step further again than the VS-EPR theory. VS-EPR was very helpful, as you remember, to give us the shapes of molecules and things, but it doesn't tell us anything about the bonding, and that's exactly where valence bond theory comes in. So it considers the interaction between the atomic orbitals to actually give us a description of how the bond works, rather than just being two electrons in between two atoms. It gives us some shape and some idea of how the bonding actually happens. And it does this through the atomic orbitals. So you can see here that we've got two hydrogens, and these are represented by the 1s orbitals. And you can see here you've got the electrons in their opposing spins. And when the two hydrogens come together to make a H2 molecule, you can see this becomes one bond with the overlap of the atomic orbitals. And the reason this is because it's described up here and through the wave function as well. When these individual electrons go together and make this sort of bond, there's no way of telling which electron came from which hydrogen. So they almost become, a collective electrons of the molecule. And because of this, the Pauli exclusion principle applies, because they are then in one collective orbital and not one or the other. So a bit like how we used to draw in the Lewis structures X's and O's to show which atom which electron came from, is not possible in valence bond theory, because it's also not possible in practice. Like, we can't tell which electron came from which atom. So the atomic orbitals merge together and then they form a sigma bond, which is from the overlap of two s orbitals. So if you go back to the sigma bond we were talking about, so if it was two hydrogens with their 1s orbitals, they'd combine to form a sigma bond, such as the example in A here. But as I was saying, it's also possible with p orbitals. So if you have the pz orbitals, they're aligned like this, like along an axis, and they can overlap here to make a sigma bond also. And the defining feature of the sigma bond is that you have this cylindrical symmetry. So if you take a line through here, through here, and rotate it like this, I can't really show it in 3D with the laser pointer, it's symmetrical, like nothing ever changes. And as well as the SS and the PZ sigma bonds, there's also an example here of HF, and this would also work for like HCl, HBr, all of these halogen hydrides. And that's a combination between S and a p orbital that we're seeing here. So you've got that electron in the 1s orbital and the 2pz, and they can also come together to form this sigma bond. So there's another type of bond as well, the pi bond, and this is typically what we'll think of as double and triple bonds as well. I'll come on to them as we go through. But so sigma bonds are generally single bonds, pi bonds are what contribute to double and triple bonding character. And this is from the pairing of electrons in two p orbitals going side by side. So we had the pz, which were lying down like this and overlapped. We've also got the px and the py. So if you say this is the px going up and down, they can overlap side to side. And then you can also get this same thing rotated 90 degrees. So it's not possible for me to draw anything, but imagine exactly what we're seeing here, but going in and out of the screen, so perpendicular to this one. And when they overlap like this, you have pi bonds, which so the nodal plane, to explain this, passing through the internuclear axis, that means that with a pi bond you have an area of bonding orbital here and one here, and a node in the middle, which is actually an area that the electrons can't be. So let's look at an example here again. So this time we're looking at nitrogen, which we also used for the Lewis model, and we saw there that it had a triple bond. And here we see the same thing. So they've both got 3 unpaired p electrons, and then they all pair to get 3 bonds, again like the Lewis model said. But this time we can see how the bonding actually works. So we've got 2 pz orbitals coming together to make the sigma bond like we showed in the last slide, and these have got cylindrical symmetry here. And then we've got 2 pi bonds being formed, the px, or the overlap of 2 px orbitals, which are kind of hidden in the middle here. And then this is the one I was trying to describe, the py, that are going in and out of the plane of the screen, slide, whatever you're looking at it on. So yeah, and this goes inside, it gets too much trying to put them all together. So you've got a sigma bond along the axis and then pi bonds surrounding it. One final thing to come to with the valence bond theory that's quite important for shape, and especially the chemistry of carbon, is hybridization. So this also helps with, as I was saying, shape. If we take methane, well, we are going to take methane as an example, but also ethene, or well, let's do it with 2 carbons each time. So ethane, ethene, and ethyne, so like with the single, double, and triple bonds, we can still describe the shape. And this is through orbital hybridization. So this comes from the combination of s and p orbitals to make hybridized orbitals that we call sp3 orbitals. And this happens, there we go, by an electron from one of the from the 2s going up to the empty 2p orbital, and then all of these hybridizing to become 4 exactly same energy, so what we call degenerate orbitals. And the energy of these orbitals is the same as the total energy of the s and the p, so sort of like a weighted average. And these 4 sp3 hybridized orbitals are directed towards the vertices of the tetrahedron, giving the shape for methane will have this, ethane also has it, but that will have 2 carbons. So if you imagine 2 tetrahedra are joined together, and most non-bonded, non-multiple bonds. And although this seems to take energy to promote an electron to a higher energy state, as is said here, this is more than compensated by the overlap with the hydrogen. So the fact that when these hybridize, it allows bonding with hydrogen, and that releases energy, and that compensates for this promotion. So that's sp3, and tetrahedrally. We can also do the same thing, which is called sp2, and this is where the double bond comes into it. So you would have 2 of these orbitals. Let's get all the pictures. There we go. So 2 of the p orbitals and the s orbital hybridize to make these sp2 orbitals, and these lie in a plane, so they're like a triangle. There's nothing coming in or out of the board this time, and there's 1 p orbital left, still in the plane again, but going up and down here. So if you imagine this time, if we're making ethene, where we've got 2 carbons with a double bond, what will happen here, if we bring this and a mirror image of it together, you'll have 2 of these overlapping in the middle, forming a sigma bond, these forming a hydrogen to each of them, and then this pz orbital that isn't hybridized on each of the carbons will overlap with each other, and then you'll get a pi bond here, which is how we end up getting this double bond in ethene. And very similarly, when it comes to ethyne, so like the triple bond, we do sp1 hybridization. So it's the s hybridizing with 1 p orbital to get these planar bonds here. And then if we do it again, if we had another c that's a mirror image of this one, you'd have the sp1 hybridized orbital here overlapping to form a sigma bond between the 2 carbons, and one forming with a hydrogen here, a CH bond, and then 2 of these px ones overlapping to get a pi bond here, and then the one in and out of the plane overlapping to get a pi bond here. And that's how we end up with a triple bond, is the sigma bond from the sp1 hybridization and 2 pi bonds from the unhybridized p orbitals. And here we have a summary of that. Single bonds are just sigma bonds, which could be s orbitals or pz orbitals. double bonds, which are a sigma bond and one pi bond. Remember, the pi bonds come from overlapping px or py's. And a triple bond, which is a sigma and two pi bonds. And then the greater the extent of the overlap, the stronger the bond. So this will have to do with like atomic radius and things like that, how similar the atoms bonding are. And then finally we have molecular orbital theory, which is the most complex one, but also the most accurate way of representing bonding orbitals in molecules. So this is actually taking a combination of the atomic orbitals and calculating how they mix and form the molecular orbitals where these bonding electrons can exist. Because it's this linear combination, however many atomic orbitals are combined, we end up with that many molecular orbitals also. And just like with the atomic orbitals, with these molecular orbitals, it means that electrons are delocalized over the whole molecule. So unlike when we showed the Lewis structure, they're not just two electrons in between two atoms, they're sort of delocalized in these molecular orbitals all over the molecule. So if you use H2 as an example, we can see how the most basic molecular orbital is created. So here we've got two 1s atomic orbitals of two hydrogen atoms, and they come together to make the H2 molecule. And we can see here this is a representation of the 1 sigma bonding molecular orbital. This subscript G, and sometimes you'll see a U, is relating to the symmetry of the orbital, but we won't go into this in detail. And as I said, they're a linear combination of the atomic orbitals. So you can see here we've got two atomic orbital wave functions. Let me get the pointer. Two atomic orbital wave functions of the two hydrogen atoms, and they're what's called in phase because they're in phase. They both got the same sign, and therefore we get like constructive interference and a constructive combination, and we end up with this molecular orbital. And you remember that the square of the wave function is the probability of finding the electrons. And you can see there are two peaks. They're most likely to be near one or other of the hydrogens, and a very big probability of being in the middle. And then, opposite sides of the molecule, very little probability. And then because we've actually got the wave function, we can calculate what the orbital looks like. So this, looks like a sphere, is the actual shape of the 1 sigma bonding orbital. Now, because of the wave nature of the wave functions of electrons, we can have an outer phase combination as well. So here we've got the same example. The shading in the book as well as on the slides is dreadful, but you'll see that one of these is slightly lighter than the other. So these are the same two 1s atomic orbitals of hydrogen, but this time they're outer phase, represented here by the negative. And what this means is the two wave functions are opposite. One's positive and one's negative, and this positive and negative don't really mean anything unless you've got these two orbitals coming together, because they're relative to each other. So these are outer phase wave functions, and therefore when you try and do a linear combination, you'll see they arrive like this. It looks very different. And when you do the square of this, because timesing a negative number by a negative number makes it positive, you always end up with positive probability, but you end up with this node. So it's actually a zero probability of finding an electron between the two hydrogen atoms when you have an outer phase combination of atomic orbitals. And then this is how we're representing this. It has this node in the middle. So a node is where you've got no probability of finding an electron. And this is then what we call the 1 sigma star antibonding or molecular orbital. And it's this star that represents antibonding. And again, you can calculate it, and this is what the antibonding orbital looks like. So again, you can see this region of no probability in the middle. And we can see here, we can do the same with the p orbitals. So again, like we saw in the valence bond theory, with the pz, they're coming end on, and they form a sigma bonding orbital, molecular orbital as well. If they're in phase, anyway, you get the bonding one. So in this case, in phase is the shading. You can see we've got a darker region here and a lighter region here. If they're in phase, they constructively interfere, and we end up with this bonding orbital. If they're out of phase, we get the deconstructive interference again, and we get these nodes again. So we can see there's no probability of the electron being in between the two atoms here. And again, here's the calculated what the molecular orbitals look like. And so this is sigma. Again, it's a sigma bond, like we had in the valence bond theory, a single bond. And again, there's the star representing anti-bonding and no star for bonding. And this is the G and the U I was talking about, the symmetry labels that we're not going to go through. So then pi bonding, we also have pi bonding and pi orbitals with combinations of p orbitals, again, that overlap side on, like we saw in valence bond theory. So really this is just taking valence bond theory one step further and giving us like a calculatable and physical quantum mechanical background of where the electrons can be. So again, in-phase combination of this side-on px combination gives us electron density above and below the atoms, much like we saw before, and this is how it's calculated. So you can see there's, they're not perfectly sausage shaped, so to say. There's a slightly higher chance of it being over one atom or the other, but a very high chance of it being in the middle also. And this is what we mean by the electrons being delocalized over the whole molecule, rather than just being between two atoms. And you can see here then, if we've got the outer phase combination again, you have this node between the two atoms, the nuclei, and then this is what it looks like here. Again, the star for anti-bonding and the no star for bonding orbitals. So this is the px example, but for py, again, like we were saying with valence bond theory, this would be rotated 90 degrees and you have exactly the same thing happening in and out of the screen. And we can build up diagrams of these molecular orbitals much like we can with the atomic orbitals we looked at in the first video. And the rules are very much the same. So the electrons go from the lowest energy to the highest energy, just like we did with the 1s and then the 2p and the 1s and the 2s, then the 2p of the atomic orbitals, the Aufbau principle. Again, each molecular orbital can accommodate two electrons, but they've got to be of opposite spin. And we'll see an example of this on the next slide. And then electrons in half-filled orbitals adopt parallel spins. So again, with the p orbitals, if you had two electrons in the 3p orbitals, they go in separate ones as Hund's rule. So let's look at the example of a hydrogen molecule, H2. So on the left and the right, we can see the atomic orbitals, the 1s ones, and you'll see here both of the electrons are given as up arrows. So we've got two hydrogen atoms, each with their one electron, and they combine, as we said, two atomic orbitals to make two molecular orbitals. So we've got the 1 sigma bonding orbital that's lower in energy here, and the 1 sigma anti-bonding orbital that's higher in energy here. And we fill it up, from the bottom up, the Aufbau principle. So we put both the electrons in this bonding orbital. And you can see here, we then use the Pauli exclusion principle. Even though both the electrons were initially up arrows, they can't both have the same spin. So then we've got opposite spin pair of electrons down here. And if you had more electrons, if you had 3, you would then put the next one in the anti-bonding orbital. So just because it's called anti-bonding, it just describes the way, it doesn't contribute to bonding, it actually weakens it, if anything. So we just build it up like that. And as I was saying, it does weaken the bond. You can work this out from bond order again. So like we had a bond order before, bond order of 1 is a single bond, 2 is a double bond, 3 is a triple bond. And we can work this out from the molecular orbitals. So it's half the number of bonding electrons minus the number of anti-bonding electrons. So here, we know that this is a single bond, the H2 bond, we've looked at it many times. But so the number of bonding electrons is 2, anti-bonding is 0, so 2 minus 0 is 2, half of that is 1, and we've got the bond order of 1, like we expect. And you can see it's unlikely to ever to happen, but to imagine if we had a H minus here, so it's got an extra electron, and we'd have H2 minus molecule, we'd have this pair of electrons here, and one anti-bonding one. We'd then have 2 minus 1 is 1, half of that is a half, and we'd actually have a bond order of a half, so it's not even a single bond, it's like, some weak attraction between them. So that's the anti-bonding offsets it. So finally, let's look at the rules again, just go over them again for forming the molecular orbitals. And this is something I didn't actually mention explicitly, but we should be aware of. Only only orbitals of similar symmetry combine. And what this means is the shape has to work. There has to be an overlap, either in phase or out of phase, to get this bonding and anti-bonding. Otherwise, it's called a non-bonding orbital. So an example of this would be, two we've got here, trying to combine a 1s with a px or a py rather than a pz orbital. Now this phases are shown quite nicely here. You can see the overlap, the in-phase overlap and the out-of-phase overlap cancel each other out. So there is no bonding at all. And the same with the 2pz and either the px or the py orbitals. You'll have the same thing. The in-phase overlapped region is the same amount as the out-of-phase overlapped region. So then there's no net interaction. Everything cancels out and you get a non-bonding orbital, nothing at all. So they've got to be the right symmetry and be combinable. And finally, we took a nice example with a H2, exactly the same atoms combining. But if you take different atoms, they're going to have slightly different energies. And the more similar they are, the more significantly they'll combine. And this is shown in the diagrams here. And size is important. So we were looking at cations and anions earlier. They've got very different sizes. And because of these big sizes, the atomic orbitals aren't going to overlap so well. So you won't get such efficient overlap, so there'll be weaker bonding. We'll actually see in the next few lectures that with anions and cations is so big, it's actually an ionic interaction rather than a covalent bond that we're looking at here. When higher shells are occupied, the inner atomic orbitals don't combine significantly. This is the same reason that if you've got something very large, like in its fourth shell, it's the valence electrons that really interact. The 1s electrons are going to be so far from each other, they're not going to combine and interact. And again, the big one that we've been saying all through, the same amount of molecular orbitals are made as the number of atomic orbitals that you start with.